converter. Three-phase half-wave converter provides high average output voltage, and in addition, the frequency of the ripples on the output voltage is higher compared to the single-phase converter. As a result, we need a filtering. For these reasons, three-phase converters are used extensively in high-power variable speed drives. This is our three-phase half-wave converter circuit. Since it is a three-phase, we have a VAN is going to start at 0 degrees, and the phase shift between each is ABN is going to start at 120 degrees, and VCN is going to start at 240 degrees. Now, let us represent this in the waveforms. This is VAN. VBN. VCN. T1 is connected to VAN, T2 is connected to VBN, T3 is connected to VCN. So we can turn on the thyristor T1 when VAN is positive. That means we can turn on this thyristor at this time, pi by 6. So we can turn on the thyristor after pi by 6. And T2 is connected to VBN. So it can be turned on after this value. 30 plus 120, it is 150. So 5 by 6. T3 is connected to VCN. So T3 can turn on when VCN is positive at 3 pi by 2. Firing angle given to T1 after 30 degrees, and firing angle given to T2 after 150 degrees, and firing angle given to T3 after 270 degrees. Then T1 can be turned on at alpha pi by 6 plus alpha, and for T2 5 pi by 6 plus alpha, and T3 3 pi by 2 plus alpha. T1 at an angle alpha. When I turn on the thyristor, this is my output across the load. This is the output. When T2 is turned on, across the T1 there is negative voltage. T1 is going to commute and gets off. That is known as line commutation. The T3 is turned on after 3 pi by 2 plus alpha. This is a positive value. Then this is my alpha. So this is turned on at here. This is the output. This is again T1 is turned on here. So this is my output. Then if I redraw that, the output voltage V0, then you are going to get output as, and here it is 0 and 0. As soon as the input voltage becomes negative, the thyristor is going to turn off by natural commutation. Then the currents will be available when the thyristors are turned on. Then the output voltage will be discontinuous when the R load is alone acting. This type of converter is not normally used in practical system because the supply current contains DC component. The frequency of output ripple voltage will be 3 times of the frequency. So these are the waveforms when R load is alone acting. We are missing the negative peaks in output voltage, and that is going to create a discontinuous output current. Now let us try to find out average output voltage for resistive load. Now from the waveforms, that VDC is given by 3 times 2 pi integral Vm sin omega t d omega t, and this is from pi by 6 plus alpha to pi only. Vm by 2 pi minus cos omega t between the limits pi to pi by 6 plus alpha. Now Vm by 2 pi minus cos pi plus cos pi by 6 plus alpha. This is cos 180, which is minus 1. So Vm by 2 pi 1 plus, sorry, 3 is missing here. 3 Vm by pi 2 pi 1 plus cos pi by 6 plus alpha. This is our VDC. Normalized value of output voltage Vn is given by 3 Vm by 2 pi 1 plus cos pi by 6 plus alpha divided by the average value is 3 root 3 Vm by 2 pi. Vn equals to 1 by root 3 1 plus cos pi by 6 plus alpha. These are output average value and this is a normal value. Now the VRMS is given by 3 by 2 pi integral pi by 6 plus alpha to pi Vm square sine square omega t t omega t under the square root. Now 3 Vm square by 2 pi. Now we have a formula that integral sine square omega t equals to omega t by 2 minus sine 2 omega t by 4. Now if you use that formula, then you are going to get omega t by 2 by 2 pi plus 6 plus alpha minus sine 2 omega t by 4 by 2 pi by 6 plus alpha whole to the power of 1 by 2. Now if you solve this, then you are going to get 3 Vm square by 2 pi of pi by 2 minus pi by 6 plus alpha by 2 minus sine 2 pi by 4 plus sine 2 pi by 6 plus alpha divided by 4 whole to the power of 1 by 2. Now 3 Vm square by 2 pi, this is 5 pi by 12 minus alpha by 2, this is sine 2 pi 0, so 0, then this term remains plus sine 3 times into 2 pi by 3 plus 2 alpha by 4 whole to the power of 1 by 2. This is what we got. Now try to simplify this. I'm taking that 3 out of the square root, so root 3, and we have 5 pi by 12 multiplied by 2 pi minus alpha by 2 into 2 pi. I'm multiplying with the denominator with all the terms plus sine pi by 3 plus 2 alpha divided by 4 into 2 pi 1 by 2. Now this is out of the square root, so root 3 we have 5 by 24 minus alpha by 4 pi plus sine pi by 3 plus 2 alpha divided by 8 pi whole to the power of 1 by 2. These are the RMS. This is the RMS, the average values of 3-phase half-wave converter for resistive load. These are the formulas used while deriving the above equations.